Welcome back. This is section 9.6, Work Energy Theorem, and there is no section like this in your textbook. So the work energy theorem, a theorem is an equation, mathematical equation that gives you a relationship between work done on an object and that object's kinetic energy. And if you remember, its kinetic energy is its energy due to to motion. And if you have a moving object, you're going to have a velocity to that object, and that object is going to have a mass. And the formula for kinetic energy involves the mass and the square of the velocity. So velocity has a lot to do with how much work was put in or how much work it takes to stop the object. So simply put, if you want to speed up an object, if you want to give it a speed, you're going to have to put work into it to increase its velocity, so that you will increase its kinetic energy. If you want to change it to slow it down, you're also going to have to put a force that opposes the motion, and so it slows it down to stop it or whatever. And so the work energy theorem describes this relationship. So the first term that you may not be familiar with is the Greek letter D, or delta. It looks like an isosceles triangle. And when you have this work energy theorem, which is equal to work is equal to the change in kinetic energy, that's the work energy theorem written out. The triangle means delta, it's a Greek letter delta, which always refers to the change in something. So the work done is going to equal the change in kinetic energy. So if I've given it speed, increased its velocity, so that I've changed its kinetic energy from what it used to be to what it is now, it was going slowly, now it's going fast, the only way I can do that is to put work into that object. Work has to be done on that object. So whoever's sitting in the merry-go-round, the only way that it's going to go faster is if people on the outside are spinning that merry-go-round. They're putting work into it, and as a result, the kinetic energy or the angular speed of that merry-go-round is increasing. So you have a change in it. So work equals the change in kinetic energy. Also, it's important to understand that it's a net work. So if you have opposing forces that in some ways cancel each other out, only the forces that are left over is going to be exerted at a distance, and that will be the work that would change the speed. So just because you work really hard doesn't mean anything gets done. If you just press up against the wall, you can push and push and push and get exhausted, but nothing ever really happens. So it's only the net force exerted over a distance, which is the work, that will change the kinetic energy. So here's your two examples. If you push a box across the floor and you give it a speed, if it has a speed, then you must have done work on that in order to change its kinetic energy from 0 to some non-zero number. Also, if it doesn't slide, then it must be that the friction force of that box against the floor is greater than the force you're pushing on it, and so there is no work done. So if you don't move if you exert a force but over no distance, then you don't have a work done, and if you haven't put work into it, you have not changed its kinetic energy at all. If you have the work done on an object is equal to the change in the kinetic energy, if you double the work, you can double the change. So if you speed something up, you can speed it up twice as much if you double the work that you put into it. Or if you slow something down, you can slow it twice as much further down if you put twice as much work into it. So as this number, since it's on the opposite side of the equal sign, is one goes up, the other goes up. The change goes up in the same proportion as the work done on it. If you're slowing down an object that's moving, one of the ways that you can change the kinetic energy or lower the kinetic energy is by applying a friction force. Now, if you have a ball just rolling across the floor, eventually it's going to come to a stop because the floor is not perfectly frictionless. The ball is not, or any object that you would slide is not. There's nothing perfectly frictionless. But if you were wanting to increase the friction in order to slow something down, say by making a brake is using friction force to change, it's doing work on an object in order to change its kinetic energy. So if you're flying down the road and you're like, oh, I'm going too fast, you put on the brakes, your brake pads engage and are rubbing against each other. that rub is slowing down the car because the work being done is reducing or is increasing the change, a negative change of the kinetic energy. So if I look here at the tire, that's if you just lock your tires and you scrape your tire across the floor, this is an infrared camera, and you can see that the floor got hot at the place where it was scraped. Now the bike is slowing down. The bike is slowing down at the same time, but the way it was slowed down is by increasing that friction force, which made work on the ground and on the bicycle, and that work done on the object slowed the object down and changed its kinetic energy. So you can see even on the bottom of the tire got warm, the bottom of the floor got warm. So losing energy to friction is what's like to be in the earth, because you're always having friction. It's the reason why you can walk across the floor. But this friction will change your kinetic energy. It will slow you down. And a lot of times you want it to be slowed. I've mentioned this before. Since work is going to be a force times a distance, and if let's say that is a brake, that you're using friction, the force of friction exerted over a distance, so you engage your brakes and you engage it over a distance, and that, this is equal to work, and that work is equal to the change in the kinetic energy. Well, kinetic energy, remember, is 1/2 times the mass of the object times the square of the velocity. So what's going to happen is the work done is going to be actually proportional to the square of the velocity. And the square of the velocity means that if I change my speed a little bit, let's say I change my speed from 5 meters per second down to 4 meters per second, 5 times 5 is 25, 4 times 4 is 16. Okay, so that's a substantial change as it's going down from 5 to 4. And so sometimes, like practically speaking, the faster you're going, the farther you will need to stop. Here's an example. If you're going 45 kilometers per hour, it's going to take 10 meters to stop if you lock your brakes. If you put your brakes completely on and you're trying to stop by friction only. If you're going 90 kilometers, which is twice as much, okay, so twice the speed of 45, it takes 4 times longer to stop, okay? If you then double it again, it's going to be up from 40 to 160 meters. So you're seeing you have a J curve. You're getting faster and faster as you're getting faster. So the bigger the change, the bigger the speed, the much more distance that you would have to cover in order to slow down. If you were in, say, an oil tanker or some kind of an enormous ship, and you locked up the engines to where there's no forward motion at all, it might go a mile before you would actually stop that boat, because your speed and your mass is both included, right? You have this, it's m, remember it's going to be 1/2 times your mass times the square of your speed. So it's not just how fast you go, but how massive you are would determine your stopping distance. So if you were to lose some of that energy that was making that object go fast, if you're losing some of it in heat, say to friction, then some of this energy it's hard to see where it goes. Like, you can't tell that the ground was slightly warmer. If you have energy of water falling over a waterfall, it's hard to tell that rock at the bottom of the waterfall got a tiny bit warmer when the water fell on it than it was before. So sometimes you can't tell where the energy goes. You just know that the roller coaster can't go from the top of the hill to the next hill as tall. So if you were to have 2 hills identical in a roller coaster, your roller coaster would not make it, because wherever it went, whether it was sound of the wheels on the track, or whether it was warmth, or whether it sparked and made some light, or whatever it was, even if you have no idea what it was, it's going somewhere. You're losing energy due to, in many cases, friction. Friction's the enemy. So let's see if you can do this one. A friend says that if you do 100 joules of work on a moving cart, the cart will gain 100 joules of energy. When is that the case? When will you get 100 joules out if you put 100 joules in? Okay, so think about that. Another friend says this depends on whether there is friction or not. So if I push with 100 joules of work, does that mean that I'm going to get 100 joules of energy out of it? Remember that if I push a box along the floor and I'm exerting it at a force, I might have an opposing force called friction that is wasting some of my energy. Some of my energy wasted in warming the floor and not putting into moving the box. So the answer would be, if you had friction, you'll probably have less than 100 joules of work that's actually converted into changing the kinetic energy of the cart. So here's a problem. When the brakes of a car are locked, the car skids to a stop. How much farther will the car skid if it's moving 3 times as fast? So how much kinetic energy does it have? What's the formula? The kinetic energy due to motion is 1/2 times the mass of the object times the square of the speed of the object. So if I make something go 3 times as fast, then I'm going to have 1/2 times m times 3v squared. Well, what's going to happen? I need to square the stuff inside that parentheses. I'm going to have 1/2 times m times 9 times v squared. And then I can move the numbers together, and I end up with 9 times 1/2 mv squared. Okay, let's compare that. I've got 1/2 mv squared and 9 times 1/2 mv squared. So if you change the velocity by 3, you're going to change the kinetic energy by 9, and the kinetic energy, remember, is equal to the distance times the force. So that means as this goes up, the stopping distance at the same amount of force of your brakes can only go as much as it can go, the distance will go up by 9. So did you learn anything? What is the work energy theorem? The work energy theorem says that the work, or the amount of work done on an object, can change the kinetic energy of that system. You can either make something go faster by increasing its velocity, or you can make something go slower by decreasing its velocity. Either case, you're going to change the kinetic energy of the system by doing work on the object or having work done by the object. So as an object is moving, let's say I've got a car or a train car. Let's say I have a train car on the track and it bumps into a car going slower than it. So you have a little tiny bit of a bumpy crash, but they don't go off the tracks. The faster car is behind, the slower car is ahead. So what'll happen? The car behind will push the other car and slow down. So you are doing work on the first car by the faster car, and it slows down the faster car. So if work is done on it, I can increase the kinetic energy, or if work is done on it backwards, like catching a baseball, that I can slow down the kinetic energy, or if work is done by an object to another object, I can slow down or speed up your kinetic energy.